In this lesson, we are going to go over applications of functions. To complete this lesson, the video will probably be broken up into 2 or 3 parts. So our goals are to apply our understanding of slope, y-intercept, and equation of lines to application problems. So the application problems will involve some of these elements. Some of them will also talk about domain and range as well. So with that, recall equations of lines in domain and range. So our equation of a line in slope-intercept form is y equals mx plus b, or using function notation, f of x is equal to mx plus b. With f of x, it means f is a function of x. X is our independent variable, and y is our dependent variable. So y depends on x. Just as a refresher, domain is our x values, or the values of the independent variable. Range is our y values, or the values of the dependent variable. And remembering these as independent and dependent variables could help us as we go through application problems. So example 1, we're just going to get acquainted with the idea of determining the independent variable and dependent variable in each scenario. So scenario 1, temperature versus time of day. So does temperature depend on time of day, or does time of day depend on the temperature? Whenever you have time, it's typically the independent variable. It waits for nobody. Okay, so this would be our dependent or our independent variable, and temperature is our dependent variable because temperature depends on time of day. When it's really early in the morning, it's the coolest, and as the noon sun comes over, it gets hotter. Okay. Number 2, distance traveled versus time. Does distance depend on time, or time depend on distance? Distance depends on time. So again, time would be our independent variable and distance is our dependent variable. Number 3, items sold versus profit. Does our items sold depend on the profit, or does the profit depend on items sold? Profit depends on items sold. So profit is our dependent variable, items sold is our independent variable. Okay. Example 2, consider the graph of the function below. So first we're going to identify our independent variable, and then we will identify our dependent variable. Okay, so independent variable, remember that is x. You can also look at it in the context of the problem. We have years and world population in billions. So our independent variable in this case is years. That means the dependent variable is our world population. Okay, and again, this is the x-axis, this is the y-axis, so that can help us determine those as well. Continued, so consider the graph. So the domain of the function is it's going to be the years, okay, because those are our independent variables, from the minimum value of, so our minimum here is 2000, or our lower year, our lowest year, and the maximum value of our highest year is 2020. Okay, so our domain is going from all the years 2000 included all the way up to 2020 included. The range of the function is the world population. Okay, so our y values from the minimum value, so we have 6.1 billion, to the max value of 7.8 billion. Okay, so that's an example of how domain and range is related to independent and dependent variables. Number 3, for the function involving the variables listed, complete parts A through C. Years since car is purchased, value of the car. So the domain. So in the homework in my math lab, you're given a scenario where you have to use your intuition or reasoning on here. So what I've put on here is just some realistic values, or one scenario of realistic values. But when you're looking at this in the homework, make sure that you are thinking about the numbers and the units given. So the domain. So the domain is all years in which the car is drivable, let's say from 0 to 20 years. Okay. Describe the range. So the range is the values of the car, or from 0 to 25,000. So in this case, the new car was $25,000. It could potentially drive for 20 years. Okay, and then a rough sketch of the graph. So when the car is first purchased, that's when it's at its highest value. Okay, and we're saying from 0 to 20 years when it reaches a value of 0. So the graph would look something like this. Okay. Let's move on into working with equations of lines. So recall again, we have y equals mx plus b, which is the slope-intercept form of a line. We can also describe it in function notation. F of x is equal to mx plus b. M is the slope, and remember, slope is also average rate of change. B is the y-intercept, or the fixed value, or you can think of it as the initial value depending on the context of the problem. X is the independent variable, y is the dependent variable. So what that means is we can rewrite y equals mx plus b as our dependent variable, which is y, slope, which is m, independent variable, which is x, and our initial is b. So this way of thinking about y equals mx plus b can be super helpful for application problems. Okay, so example 1. So the cost in dollars of driving a rental car x miles is given by c of x is equal to 1.60x plus 40. So we're just going to walk through breaking apart this equation, okay, to help us get acquainted with applying linear functions to applications. So the independent variable, so x is our independent variable, but what does it represent? It represents the number of miles driven. Okay, our dependent variable is our cost. Okay, our cost of driving this car depends on how many miles we drove. Okay, what is the slope? Again, this is in the form of mx plus b. So m is 1.60. And what does slope represent in the context of this problem? Okay, so a slope is a rate of change. So in this problem, our dependent variable is cost, and our independent variable is miles driven. So it's going to be cost miles. Remember that slope is change in y over change in x. So our dependent variable, or a change in our dependent variable over a change in our independent variable. So the units are dependent variable over independent variable. So it costs $1.60 per mile driven. So that's what it represents. So if you drive 0 miles, there's no cost. If you drive 1 mile, it's 1.60 times 1, 2 miles, 1.60 times 2, and so on and so forth. Okay, so a better way of writing this is $1.60 per mile. What is the y-intercept? So the y-intercept is the b value is 40, and what does it mean in this case? That this is the initial cost or the fixed cost. Okay, so notice you sign the contract and you decide not to drive the car anywhere, you're still paying $40. Okay, or if you drive the car 100 miles, we still have this plus 40. Okay, so that's a fixed cost of this rental car. Okay. So number 7, how far could you drive with $112? So you have to decide, is 112 cost or is that miles driven? It's cost. So we would put it in place of c of x. Okay, it's also asking how far, which means that it's looking for x. So we would solve this like we would any equation. So we would subtract 40 from both sides. And I'm going to use my calculator to make sure I get it right. 72 is equal to 1.60x, and then we divide by 1.60, divide by 1.60, and we get 45. Okay, so this is 45 miles. So what this means is that you can drive 45 miles with $112. Okay. Question 8, if you drive 400 miles, what will the cost be? So in this case, we're given x. Remember, x is number of miles driven. And now we're looking for cost. So we're looking for c of x when x is 400. Okay, so we're finding c of 400. That would be equal to 1.60. Okay, remember it costs $1.60 per mile. So if we're driving 400 miles, it makes sense that we're taking 1.6 times 400 plus 40. Okay, so we put this into our calculator. 1.6 times 400 plus 40 is equal to 680. Okay, so what this means is that it costs $680 to drive 400 miles. Example 2, find and interpret the average rate of change from the following graph. Okay, so average rate of change is another way of saying slope. Remember that slope is y2 minus y1 over x2 minus x1, or in terms of independent and dependent variable, it's our change in dependent variable over our change in independent variable. Okay, and I've kind of abbreviated those just so that they fit on the screen. Okay, so we have price per gallon of gas in dollars. So we've got a couple of ordered pairs here. In 2018, the price was $3.19. And in 2021, the price was $3.90. Okay, so what we can do then is we can plug this into slope. So y2 is 3.9 minus y1, which is 3.19, over 2021 minus 2018. Okay, so if we put this in, we would get, so 3.9 minus 3.1 is 0.71 divided by 3. If we divide this, we get 0.236 and so on. Okay, I didn't tell you where to round, but since it's money, we'll round to the cents place. So we would get, 0.24. Okay, now remember our units. We've got price per year. So this is 24 cents per year. Okay. So the price of gas, if we're talking about this in terms of rate of change, so the price of gas is increasing because my line is going up, or the price is higher in 2021 than 2018, is increasing by, or increasing 0.24 each year during these years. Okay, so average rate of change, when you see that, you want to think of slope. We will stop here for now, and in the next lesson, we'll continue modeling with linear equations.